Okay, we have been looking at Pauli flow. We are talking about Newtonian incompressible fluid flow through microchannels of long microchannels of constant cross sectional area, which is called Pauli flow, right. In Pauli flow, the flow rate is directly proportional to the pressure difference. Okay. So, knowing that, we can establish what is called hydraulic resistance. Okay. Let us look at what is called hydraulic resistance. So, in Pauli flow, we can write delta P will be equal to R hydraulic into Q. Okay. So, here delta P and Q are proportional to each other. So, you can write delta P is R hydraulic into Q. So, this is known as hydraulic resistance. Okay. And the inverse of hydraulic resistance is known as hydraulic conductance. Okay. So, what we see here is the Hagen-Poiseuille law, which is delta P equal to R hydraulic into Q, is similar to Ohm's law. In case of Ohm's law, the voltage difference is the product of current and resistance. Okay. So, Pauli flow is equivalent to Ohm's law, which is delta V equal to I into R. Okay. Now, the concept of hydraulic resistance is very important in microfluidics, because it helps in characterizing microchannels, it helps in designing microchannel networks. Okay. So, the concept of hydraulic resistance has practical importance in microfluidics. Okay. We have another terminology called hydraulic compliance, okay, equivalent to capacitance in an electrical circuit. In hydraulics, the equivalent term is called hydraulic compliance. Okay. So, hydraulic compliance is equivalent to the electrical capacitance, and the hydraulic capacitance is defined as change in volume over change in pressure, and there is a negative sign, okay, because the volume is usually reduced when the pressure is increased. Okay. So, this term is called hydraulic capacitance, okay, denoted by C. Now, let us look at viscous dissipation equivalent to Joule heating in electrical circuits because of finite resistance and finite current. In hydraulic circuits, we have viscous dissipation. When you have a flow Q is occurring because of the pressure difference delta P, we would have a viscous dissipation. Let us imagine we have a tube and we apply at time t less than 0, we have a pressure difference delta P between the two ends, and let us say at time t equal to 0 we take out that delta P. Okay. So, what will happen is the initial energy will get used up to give rise to the viscous dissipation. Okay. So if you look at this case here, so let us consider we are talking about viscous dissipation. Let us talk about flow between parallel plates. So let us say this is the inlet, this is the outlet, we have pressure here P star plus delta P and pressure at the outlet P star, and this is at time t less than 0. So you get velocity V equal to some V0, right. Now at time t equal to 0, let us say you take out the pressure drop delta P, now this pressure will be equal to this pressure, right. So initially the velocity profile, as you know, it will be parabolic. At time t equal to 0, when you just take out the delta P, the profile would still be parabolic, okay. But as time progresses, let us say time t greater than 0, here V will also be equal to V0. When time progresses, let us say this is P star and this is P star, the velocity profile will become smaller, okay. So it will become flatter, right. So this V is going to be less than V0. Now as time t tends to infinity, you will have same P star here and P star here, and the velocity will become 0, right. So the energy of the fluid is utilized to overcome the viscous loss, okay. So the viscous dissipation can be expressed as W viscous is expressed as Q into delta P. So delta P is the pressure difference here and Q is the flow rate that is occurring. So if you take out delta P, that energy will be utilized to overcome the viscous loss, okay, and that actually helps us to understand the hydraulic resistance, okay, because there is a finite resistance offered by the walls, the viscous dissipation occurs and the energy is dissipated to overcome the viscous dissipation, okay. So let us consider hydraulic resistance in case of a a circular channel cross section. So we first consider hydraulic resistance analysis, and first we consider circular cross section. Okay. So we have, let us say, a hydraulic circuit, something like this. Here pressure is P0, here pressure is P1, this is hydraulic resistance and we have flow Q occurring, okay. So the pressure difference delta P is going to be P0 minus P1, and from Hagen-Poiseuille law what we have seen here, okay, this is called Hagen-Poiseuille law. we can write delta P equal to P0 sorry Q into R hydraulic. Okay. And for a circular channel we know that Q is pi R4 over 8 eta L into delta P, and pi R square is the area, so you can write it as A R square into delta P divided by 8 eta L, right. So this is the hydraulic resistance. Okay. So R hydraulic is going to be 8 eta, so this is actually 1 over R hydraulic 8 eta L divided by A R square. Okay. So this is the expression for hydraulic resistance for circular channel. Now let us look at here hydraulic resistance of different channel cross sections. First look at the circular channel cross section, and here the hydraulic resistance is what we just obtained, 8 eta L over A R square, which is pi A4, A being the radius of the circle. And if you consider A is 100 micron, we can see the hydraulic resistance is about 0.25 into 10 to the power 11 Pascal second per meter cube. Okay. Now if you consider an elliptical channel where A is the half of the major axis and B is half of the minor axis, A to be 100 and B to be 33 micron, then the hydraulic resistance is going to be 3.93. Okay. And if you look at triangular cross section, you know the hydraulic, this is the expression for the hydraulic resistance, and if you compare with that circular cross section, this circular cross section has radius A, and here the triangular cross section has each side A, you can see that the hydraulic resistance is about 70 times the circular cross section. So hydraulic resistance of a triangular channel is very high. Okay. Now if you look at two parallel plates, the hydraulic resistance is given by this expression here, and this is its value when we talk about a separation distance of 100 micron. Okay. And for all cases we are considering viscosity to be 1 millipascal second, right. Next, for the rectangular cross section, this is the expression, and it is not very different compared to the parallel plate case. Okay. The resistance is not very different. In case of a square channel cross section, you can see this is the expression here, and for a square cross section of each side 100 micron, the resistance is 2.84. It is definitely higher than the circular cross section, but lower than the triangular channel cross section. And here is the expression for the hydraulic resistance in case of parabolic channel, and this is its value when H and W are given here. Okay. H is 100 micron and W is 300 micron. Now this is the general hydraulic resistance that we had derived when we talked about partially flow in arbitrary cross section. Okay. So with that, let us move on to talk about shape dependence of hydraulic resistance. How, if you know the shape of a channel, how we can determine its hydraulic resistance. Okay. So we talk about shape dependence of hydraulic resistance, okay, shape dependence of hydraulic resistance. We can write, let us consider an arbitrary channel shape. Let this surface be d omega, and the inside cross sectional area is omega. Okay. Now the area A can be written as integration dx dy integration over omega using Cartesian coordinate system. The perimeter P can be written as dl integration over d omega. Okay. Now we can come up with a natural expression for hydraulic resistance if you look at the circular channel case, the hydraulic resistance is varying as eta L over A r square, right. So which is eta L over S square, right, because the area is pi r square. So this is how it is varying, right. So we can write a natural expression for hydraulic resistance to be, let us call it R hydraulic star, to be eta L over S square. Okay. So where L is the channel length and A is the cross section. Since we are talking about flow through channels where on the channel perimeter no slip boundary condition will be valid, then we can intuitively think that the hydraulic resistance will be related to the channel perimeter as well as the cross sectional area. So we need to correct the natural expression for the hydraulic resistance. So we include what is called a correction factor. So we include a correction factor beta, which is R hydraulic divided by R hydraulic star. Okay. So that will be S square over eta L. So that is how we define the natural hydraulic resistance into R hydraulic. Okay. Now we can write the relation between delta P, the velocity field u, let us say y z, and beta. So delta P would be R hydraulic into Q, which is beta into R hydraulic star into Q, which will be beta into R hydraulic star integration dx dy dz u yz. Okay. So that is how you can relate delta P, u and beta. Now in microfluidics, the Poiseuille flow is coupled with many additional phenomena. Most of them are surface phenomena. For example, electrophoresis, electroosmosis, dielectrophoresis, these are surface phenomena. So in addition to Poiseuille flow, these surface phenomena are going to be important. So this is because of the high area to volume ratio at microscale. So, in that perspective we define a parameter called compactness. Okay. So, we define a parameter called compactness, which is C equal to P square over A. The ratio between square of perimeter divided by area of cross section, and this correction factor beta is the ratio between the hydraulic resistance divided by the natural hydraulic resistance. Okay. So, now here our goal will be to relate the correction factor beta with the compactness C, so that for any arbitrary cross section, if you know what is going to be the shape of the cross section, we know what is going to be the value of P square over A. So, we know the compactness. Knowing compactness, we should be able to find out beta and hence the hydraulic resistance. Okay. So, here our objective is to find relationship between beta and C. Okay. So, this will allow us to, if we know C, then we can calculate R hydraulic. Okay. Let us first take an example of elliptical cross section. Elliptical cross section. In an elliptical cross section, we can write beta, the correction factor, to be R hydraulic divided by the natural hydraulic resistance, R hydraulic star, which can be written as, so we know an expression for, we have an expression for hydraulic resistance from the Pauli flow. So, we can write it as 4 by pi into eta L into 1 plus B by A square divided by B by A cube into 1 over A4 divided by eta L into 1 divided by pi A B square. Okay. So, this is the natural hydraulic resistance, which is eta L over A square, and area of an ellipse is pi A B, right. This is what we know. So, this is the expression for the correction factor. So, if you simplify, you get 4 pi into A by B plus B by A. So, this is the correction factor for an elliptical cross section. Now, for a circle, if it is a circle, then beta will be 8 pi, right, A equal to B. So, beta will be 8 pi. So, we can write the compactness for elliptical cross section. Compactness C is P square over A. If you can represent the expression for the perimeter of an ellipse in terms of an equation and divide with the area of cross section, right, and then we have an expression for beta and we try to represent C in terms of beta. So, you would have compactness as a function of beta, right. This is the equation we end up with, 1 over 2 pi square into 0 to pi d theta into beta plus beta square minus 8 pi square square root, then into cos theta whole square root square. Okay. So, that is the expression for, if we can write an equation for the perimeter and then divide by the area of the ellipse, and then try, since we have an expression for beta, try to express compactness in terms of beta. Okay. So, this is the expression we will end up with, right. Now, if you expand C beta, if you expand this expression for C beta in beta around beta equal to 8 pi, okay. So, this is a expansion that you have to do, and then do inversion. So, now here you are expressing compactness in terms of beta. So, I am asking you to invert, means beta in terms of compactness. Okay. So, if you do that, you would get beta in terms of C as 8 by 3 C minus 8 pi by 3 plus a term which is of the order of C minus 4 pi square. Okay. This is the remainder term that you would get. Okay. So, this is the expression for correction factor in terms of compactness for an elliptical cross section. Now, if you check this for a circular cross section, our C is p square over a, right. So, we have 2 pi r is the perimeter square over pi r square. So, we get 4 pi, right, and beta for circular cross section we have calculated it here, it is 8 pi. So, beta is 8 pi. Now, if you use this equation, okay, so beta for C is 4 pi, then we get 8 into 4 pi divided by 3 minus 8 pi by 3. So, you get this as 8 pi. Okay. So, this expression is holding true for circular cross section as a special case of ellipse. So, this is a general expression that can be used for any elliptical shape. If you know what is the compactness, we can find what is its hydraulic resistance. Now, if you look at you know the plot here, in the x axis we have compactness C, and the y axis we have the correction factor beta. If you know the correction factor, you know hydraulic resistance. So, what you see here is for elliptical cross section, this is the line, okay, sorry, this is the line here is for elliptical cross section, and you see that beta is linearly dependent on C. Okay. So, the correction factor is linearly dependent on the compactness. Okay. So, that is what we see that beta is linearly dependent on C. Okay. So, next we look at a rectangular cross section. So, we look at rectangular okay. Now, for rectangular cross section we can write beta to be R hydraulic divided by the natural hydraulic resistance R hydraulic star. So, R hydraulic can be obtained by Q over delta P, right. So, we have an expression for Q for rectangular cross section, which is a Taylor series, right. So, we can divide that with R hydraulic natural. So, we get an expression which looks like this, we get pi cube, and if we say the aspect ratio of the rectangular channel, okay, we say width divided by height equal to, let us say, gamma, we will write pi cube into gamma square divided by 8 into Taylor series n or infinity into n gamma divided by pi n 5, okay, into minus 2 divided by pi square n 5 into tan h, tan hyperbolic of n pi gamma over 2. Okay, so, this is the expression we get for the correction factor beta. Now, we can find out compactness C gamma as perimeter square over area. So, this is 2W plus 2H, that is the perimeter, divided by area is WH. So, we can write this as 8 plus 4 gamma, gamma is the width to height ratio, plus 4 over gamma. Okay. So, this is the expression for C in terms of width to height ratio. Okay. So, now we know that tan of Hx equal to 1 or x greater than 1. Now, if you use that, we would be able to simplify this expression here. Okay. So, if you use this condition, then you can write that beta of gamma will be equal to 12 pi 5 gamma square divided by pi 5 gamma minus 186 into gamma to the power 5. Okay. So, we will get an expression, simplified expression for the correction factor, and this is for gamma greater than 1. Okay. So, now if you substitute this C gamma, okay, so you find out gamma in terms of C and substitute in this equation here for beta, what you get is, so you find out gamma in terms of C, okay, function of C, and substitute in this equation, you get beta C is going to be 22 divided by 7 into C minus 65 by 3. So, you substitute here and then expand C gamma in gamma around gamma equal to 2 with C of 2 as 18, which you can check here. Okay. So, if you do an expansion of this after substitution, you would get 22 beta equal 22 by 7 C minus 65 by 3 plus a term which is of the order of C minus 18 square. This is the additional term that you would get. Okay. Now, if you consider a square cross section, for a square cross section gamma is going to be 1, right. So, if gamma equal to 1, then you can evaluate what is going to be C here, right. You can evaluate what is C. C is going to be 16, right. So, C is going to be 16. So, the beta is going to be 22 into 16 divided by 7 minus 65 by 3. So, that will come around 28. Okay. And this is what we had seen for a square cross section, right. So, for a square cross section R hydraulic will be equal to beta into R hydraulic star. So, this will be equal to 28 into eta L over A square. For a square cross section it will be A4, okay. Thus A is each side. This is the expression for square cross section, and this is what we saw here, right. This is what we had seen in here. For a square cross section, the hydraulic resistance is about 28.4 eta L over H4, right. So, now let us consider a triangular cross section. Before we move on to triangular cross section, we can check in the plot here, we can see here that for a rectangular cross section, which is this line here, for irrespective of the value of W and H, beta is going to be linearly dependent on the compactness C. So, that is what also we predicted from theory. Okay. So, for a triangular cross section, we do not have an explicit expression for beta. Beta can only be determined from simulation. Okay. So, cannot be, so beta cannot be determined theoretically, and using simulations beta is found to be 25 divided by 17 into C plus 40 square root of 3 divided by 17. Okay. So, this is for a triangular cross section how beta is related with compactness. So, here C is given as 8 into A plus B plus C whole square, where A, B, C are each sides of the triangle, divided by half into A square plus B square plus C square whole square minus A4 plus B4 plus C4 square root. Okay. So, this is the expression for C, which you can find for any triangular cross section. Okay. So, So if you look at so once you know beta, you can calculate R hydraulic, right. Knowing a triangle, you can calculate compactness. Knowing A, B and C for a triangle, you can calculate compactness, and for that triangle, once you know the compactness, you can find out beta using this formula, and then you can calculate the hydraulic resistance. Now you can look at this plot here. For irrespective of the shape of the triangle, it may be right angle triangle, it may be isosceles triangle or acute obtuse angle triangle. All the different triangles fall on a same line, okay. All different triangles fall on a same line, okay, and where beta is going to vary with the compactness in the same way, okay. That is what we see here. So what we see here is relation between beta and C for different triangles fall on the same line, okay, on the plot. So with that, let us move on and talk about Reynolds number in case of a flow when we talk about two different length scales, okay. Let us consider flow between parallel plates, and when we are considering flow in the x direction, okay, then the Reynolds number can be determined based on the length of the plate, okay. But if you have a non-zero velocity component in the vertical direction, then the Reynolds number can be based on the gap between the two plates. So in this situation where we have two different length scales, what is the correct way to determine Reynolds number, okay. So we look at Reynolds number in case of system with two length scales, okay. So we have seen this infinite parallel plate case. We have two parallel plates, and this is H, this is P star plus delta P, this is delta P here, and this is 0, and we get a velocity profile something like this, okay. So here let us say this is x direction and this is y direction. So in this case we know that there is no variation in the velocity along the x direction, okay, and only y and z direction are important, okay. So we say that velocity is along x direction, so y and z directions important. Now although the system is invariant along the x direction, if we consider that we have a non-zero velocity along the y direction, then in that case we cannot neglect the x direction, okay. So when we have a velocity, let us say w coming in along the y direction, then the x direction independence breaks down, okay. So in that case the governing equations will get modified, right. So, let us do some scaling. So, we have two length scales here, one is L, the other one is H. Okay. So, we can say x equal to L into x star, okay, by inverse scaling, and we can say that Z equal to H into Z star, right, and where we can say that the aspect ratio is going to be H over L, which is going to be less than 1. Okay. So, this is what we can say. Now, this is here we are taking this as Z, that is why we have Z equal to H Z star, right. So, and we assume that in the y direction the length is infinite. Okay. So, in that case we can write the derivatives del over del x to be 1 over L into del over del x star, right. We can write, so this also we can write it as, we can write this one as epsilon over H into del over del x star, right. So, and we have del over del Z can be written as 1 over H del over del Z star. Now, the characteristic velocity along x direction, so x direction characteristic velocity u0, okay, will be q divided by w into h. W is the width of the plate and h is the gap between the plates, and the characteristic time can be t will be equal to, let us call it t0, will be L over E0. So, and we can say t equal to t0 into t star. Okay. Now, we can write the velocity components, u as u0 into u, right, and you can write w will be equal to h over t0 into w star, right. So, this is u star, u0 into u star, w equal to h over t0 into w star, which will be equal to epsilon u0 into w star. Okay. Epsilon is h over L and L over t0 is u0. So, we get epsilon u0 into w star. The characteristic pressure, this is characteristic time, this is characteristic velocity components. Characteristic pressure P0 can be written as R hydraulic into Q, which will be equal to eta L over WH cube, this is the hydraulic resistance in parallel plate flow. There is a factor 12, but we are not considering here because we are doing a scaling here, into Q. So, that will be equal to eta u0 L over h square. Okay. Now, if we follow the convention that the Reynolds number can be defined based on the smallest length scale, then we can define Reynolds number Re as rho u0 h over eta. Okay. but here we have 2 length scales. So what we will do is, if you write down the Navier-Stokes equations using all the non-dimensional terms here, okay, we would have 2 different momentum equations, because we have 2 different components of velocity now. So we can write Navier-Stokes equation. One, it will be epsilon into Re into del over del T star plus U star del over del X star plus W star del over del Z star into U star will be equal to minus del P star over del X star plus del square over del Z star square plus epsilon square del square over del X star square into U star, and the second equation will be epsilon cube Reynolds number into del over del T star plus U star del over del X star plus W star del over del Z star into W star will be equal to minus del P star over del Z star plus del square over del Z star square plus epsilon 4 del square over del X star square of W star. Okay. And we have the continuity equation as del U star over del X star plus del W star over del Z star to be 0. Now here, if you in the limit when epsilon tends to 0, which is the case when the gap between the plate is small compared to the width of the plate, then in that case if you see here, this term is cubic, okay, this is 4. So all this term as well as this term are going to vanish. So you have only pressure gradient term present here, and in this equation there will be no change. So what we see here, since these terms will vanish because epsilon is very small, instead of Reynolds number, epsilon into Reynolds number appears as an important parameter. So this is called effective Reynolds number. Effective Reynolds number for 2 length scale problem is here, Re effective is going to be epsilon into Re, which is rho U0 H divided by eta into H over L. Okay. So this is rho U0 H square over eta L. So that is how we can express Reynolds number for 2 length scale problems, and here the effective Reynolds number will be small compared to the actual Reynolds number, because it is multiplied by H square, okay, multiplied by epsilon, which is very small compared to 1. Okay. So we stop here.